Let's start our plenary talk number 3. Thank you, Dr. Daniel Nunes. He will deliver the presentation from the US, and he will talk about planetary, the use of radar in planetary section, science from the surface on downwards. Daniel Nunes, the floor is yours. Thank you. Thank you very much.
Thank you, Fernando. Thank you, everyone, for inviting me to participate in this workshop. It's really an honor to be presenting to this group today. Thank you, Professor Hugo, for everything that he's done to this day in our growing collaboration. So I see that you can see my screen. I'm going to switch screens here. And do you see it in full screen mode?
Not yet. Full screen?
Is it in full screen?
Yes.
Excellent. Okay. Thank you. So the first order of business here is, first of all, I need to apologize because the plan was for me to be there in presence, but there are a lot of things changing right now in terms of the priorities of NASA. There's a lot of focus on Moon and Mars, and there's some new proposals that are happening here, and I just couldn't move for a week and to be down there because I'm being requested to participate in something here at work. The other thing is that my employer requires that I say that I'm representing myself alone, and all the content here in this presentation is publicly available, and the opinions expressed here are strictly my own. The next thing is that planetary science, the use of radar in planetary science, is at least a topic that would need a full semester in a college course or in a graduate course to really go at depth. So here, what I'm intending to do today is to give just kind of a wide brush of how radar has been used to determine different things about the planets, other than our own, of course, a little bit of history and scientific context, and the things that are coming up in the near future for planetary radars. And finally, I'm a terrestrial planet kind of person, so my interests lie on Earth, Moon, Mars, Venus, and there's a whole lot of material and exploration done at the icy satellites about the giant planets in our solar system that is being done. And I'm not going to touch on those because otherwise it just wouldn't really fit in the time allotted for this presentation. So my focus is going to be strictly on the terrestrial planets. So in the beginning, how this all started, it dates back to 1946. And this is the front page of the New York Times dated January 25th of that year, with a headline of "Contact with Moon Achieved by Radar in Test by the Army." So it was not even 6 months after the end of World War II, and I think people were really tired of just...
Dr. Daniel, I think you are changing slides, right?
Yes, I am changing slides. You're not seeing that?
No, we are just...
Okay, stand by. Let me reshare here. Stop sharing. And let me change windows here. Stand by. Almost there. Let me reopen the software here. Yeah, I'm really not used to Google Meet. Allow share screen. All right, are you seeing my screen again? Yes, you are. Let me open PowerPoint. And okay. Are you seeing my screen with a presentation now?
Yes.
Okay, excellent.
Yes.
So
Perfect.
Yeah.
is it changing?
Yes.
Excellent. So these are the things that I talked at the beginning, the first order of business, and how did it all start back in 1946? So front page of the New York Times, showing the date of January 25th. It was not even 6 months after the war, and people were starting to do very interesting things with all the knowledge that they developed during the war. I think in part they were so tired of just fighting that people were curious and eager to do other things. So this group at the Army, in collaboration with the Army here in the United States, they adapted a new military radar. In fact, the same kind of radar system that saw the airplanes come into Pearl Harbor earlier in the 40s. They adapted this radar and its antenna and sent some signals to the moon on January 10 using 111 megahertz signal. And it used an antenna that was an 8x8 array of half-wave dipoles that was steerable in azimuth but not in altitude, so they had to wait for the moon to be in the rising or in the setting position. And that antenna had a gain of 250. Here are some parameters of the radar, which was modified from this wartime radar, and they had a 3 kilowatt equivalent power. Now, the distance between the Earth and the Moon, and you can see here at the top of the slide, I put everything close to scale, the size of the Earth, the size of the Moon, and their separation in scale, is 383,000 kilometers. So when you do the spherical wavefront spreading to and back from the Moon, this is equivalent to a minus 241 dB loss. So the signal that they had to observe in return was really, really faint. So the adaptation of the radar and the antenna really allowed them to do that for the first time. And they accomplished the range measurement to the moon just by time delay. And of course, one of the curiosities at the time was whether trans-ionospheric communication would be possible, and they showed that that was indeed the case. Here's the team that did that first step in the exploration of the solar system with radar, using active radar. So it was a mix of civilians and the colonel, lieutenant colonel there in the middle. So that was the team. And of course, that started radio astronomy in terms of the active radio astronomy. And of course, there are many radars that have been used since, ground-based radars like the one in Goldstone here in California, which has a 70-meter antenna, Green Bank in the east coast of the United States, and now the now deceased Arecibo 300-meter antenna. Of course, we have the big ground-based dish in China that is now 500 meters in diameter, starting to do radio astronomy work. So that's how it all started in terms of sending radar pulses to investigate the planets. And here's just an example of a modern observation, ground-based observation using bistatic 70 centimeter wavelength to image the moon. And this bistatic image was transmitted from Arecibo, the big antenna here, and received at Green Bank. And the yellow line here is going to show up in a future slide that I'm going to show, so I'm putting here just in context. And this is Mare Serenitatis, which you can see here in the image of the moon. It's that area there, that one big impact basin that was later filled with lava to form the Mare. So the 70 centimeter image penetrates the lunar subsurface by several meters at least. And what the backscatter is showing here is different lava flow units on the surface of the Mare, as well as the ejecta blanket around the large craters. So even from ground base at 383,000 kilometers of range, the instrumentation is so sensitive that we're able to do quite a bit of science just from radio astronomy alone. Now, the next big step in terms of planetary radar using active radars happened with the Apollo program. The Apollo 17 in 1972 had two types of radar instruments, and they wanted to accomplish imaging and subsurface measurements of the moon. The first instrument was the Apollo Lunar Sounder experiment, which was attached to the command module, which remained orbiting the moon while the other astronauts went down to the surface. So this was an orbital sounder. The second instrument went down with the astronauts to the surface, and it was essentially an in situ precursor to ground penetrating radar. And I'm going to talk a little bit about those two. So here is the lunar sounder experiment. Here's the command module, and the lunar sounder had three channels, three modes of observation. You had a high frequency HF1 and HF2 at 5 and 15 megahertz for deep and shallow sounding. And those two modes used the dipole antennas that protruded from the sides of the command module, and those were 10-meter antenna elements. For imaging the surface and a little bit of penetration as well, they used this VHF system at 150 megahertz, which had a 16 megahertz bandwidth, and that system used a Yagi antenna that was rotated from nadir pointing. So the rotation helped solve the problem of left-right ambiguity that we have in radars. Nadir-looking sounders. So this system innovated in the sense that it transmitted a linearly modulated frequency chirp pulse that had a finite duration and employed pulse compression to generate a narrow series of echoes of the surface and the subsurface. The problem with, as we all know here, we're radar people in this room, the problem with pulse compression is that you have side lobes. And if you have a shallow subsurface reflection, as I'm showing here with my cursor, that is quite close to the main lobe of the surface reflection, the side lobes can mask the main lobe of a subsurface reflection. So there are a variety of techniques that we employ in terms of windowing of the pulse to try to mitigate side lobes and eke out the faint subsurface reflections. So this was the first sounder to be sent to the planet. Then there was here's one more thing about the lunar sounder that was in orbit. It aimed at obtaining subsurface soundings and subsurface profiles, synthetic aperture imaging, as I said, and also measure radar albedo, so they could do some calibrations and computations of material properties. The other thing about sounders that is ever present is the issue of clutter. So if there's enough dynamic range in the topography of the planetary surface, the earlier arrival may not be from nadir, but from one of the sides. So when you plot this in a radargram, it can be somewhat confusing in terms of what is surface and what is subsurface. So there lies a need for understanding the planetary surface topography for us to properly interpret the radar soundings. And here is the same profile that I showed in an earlier picture in the Arecibo data. This is a photographic image of the same area of the moon with the Apollo Lunar Sounder profile and the earlier sounding that Apollo 17 obtained of the subsurface. So it was able to see subsurface reflections of different layers in the mare, and the wrinkle ridges here, and the ring of peak that lies beneath the lava that has solidified to form the mare. So this was quite a successful experiment, even though the technology at the time was, by today's standards, somewhat limited. Now, for the surface electric properties experiment, the precursor of ground penetrating radar, They had a bistatic configuration where they put the transmitter and antennas on the ground and then the receiver on the lunar rover, and they drove away from the transmitter as the transmitter was emitting signals. So of course that created multipath. You had direct waves in free space to the antenna. You had refracted waves from the surface layer and out again to the antenna, and subsurface reflections. And what these interferograms, sorry my spelling here, misspelling, but what you can have through these multipaths are interferograms, which you can later invert for layer properties of the subsurface. So here's some in the middle, some modeled interferograms. And on the right here is the model interferogram for a layer over a half space. And here's the data in the bold curve. So they were able to extract some information of the subsurface, and they used different wavelengths or frequencies for deeper penetrations from 1 megahertz to 32 megahertz. And inverting the signal from this experiment, earlier on, they were able to show with a very basic inversion layer over half space type of structure of the subsurface, where the layer has an increasing dielectric constant, which is here on the x-axis, and y-axis here is depth. And you see that an average dielectric constant for that top layer is about 3.5 relative dielectric constant, and the half space here is more like 6.25 dielectric constant. A more recent reanalysis of the SEP dated using different techniques provided these two profiles as well, the blue and the red, depending on the inversion technique. And our current understanding of the lunar subsurface at Mare is that you have the top layer of regolith, this very finely powdered material created by millions of years of impacts, over this fractured Mare lava, and then the layer lavas that form the Mare, and then the original crust of the moon beneath, which is called the regolith, where it's all cracked, and then down lower you have a solid anorthosite for the lunar crust. So an early, very basic experiment that yielded already information about the lunar subsurface. And here are two photos of the receiver on the rover here on the left. And I don't know if through Google Meet you can see, but here's the transmitter, and there are 3 wires, which are the antennas. They're red, one coming this way, one going that way, and one normal to them. So that was another big step in using radars to understanding the planets. In 1978, there was another breakthrough, and he started a series of observations of the planet Venus. It was the Pioneer Venus orbiter mission to Venus. It carried a radar mapper. And Venus is one of these places which is ideal to use radar, because Venus, as you see here on the right, is a planet that is completely covered by a thick and opaque cloud layer. So you cannot use visible wavelengths to observe the surface. Radar is it. There are some windows in infrared and near infrared that you can use to image the surface, but there's so much scattering in the atmosphere that the images in infrared are very fuzzy. You cannot get details from the subsurface. That's another limitation. So radar is the perfect technique for observing Venus. So the Pioneer Venus orbiter, as you see here on the right, carried this radar mapper instrument. The radar antenna is this little dish here that is in its stowed position, and used L-band 17 centimeter wavelengths, and mapped from an elliptical orbit that changed quite a bit in altitude. And it generated images that had resolutions between 20 to 40 kilometers per pixel of the surface. So it wasn't very very detailed. It was better than anything before, of course. It was groundbreaking, but to do geology from orbit, 20 to 40 kilometers, is somewhat limited. It also collected altimetry data that had a 10 to 50 kilometer in pixel size and an uncertainty level of plus or minus 200 meters vertical. And it was side-looking, had a range of side look angles of 30 to 58 degrees. But the great thing about Pioneer Venus was generated near global coverage. So it provided the first detailed map of the surface in terms of topography. It showed that, unlike Earth, where you have the basins for the ocean basins and the higher continents, the bimodal hypsometry, we say, for Venus, it showed a uniform distribution that had just one peak, so a unimodal hypsometry for the topography of Venus, which is quite interesting because it's not like Earth's. It imaged this enormous volcanic plateau of Ishtar Terra, where the highest elevations on Venus are found, and also mapped the tectonically disrupted Aphrodite Terra. They thought it was radar bright, but they did not know quite why, because the resolution of the data was poor, and imaged the radar dark plane. So here are two maps produced by the same map, actually, produced by PVO. The only difference between the top and the bottom is the stretch of the grayscale. So the radar dark are the plains, and the radar bright are the highlands. So here, this area between 60 and 150 degree longitude is Aphrodite Terra that has very high backscatter. And here's the topographic map. You see Aphrodite Terra as a highland, several kilometers above the mean elevation of the planet. And here's the big plateau of Ishtar Terra, with Maxwell Montes being the highest point on Venus, about 11 kilometers elevation above mean planetary radius. So PVO was groundbreaking. Following PVO, in 1983, there was Vignetta 15 and 16 from the Soviet Union, which used shorter wavelengths, now from L to S band now, and it vastly improved the resolution of the imagery data from what PVO had by over an order of magnitude. The image resolution was 1 to 2 kilometers. The altimetry was similar to PVO, a little bit better in terms of uncertainty. But the orbit was much more elliptical. So what happened was that the data set from Vignetta 15 and 16 covered only the northern hemisphere of Venus. It was not a global coverage. But it provided the highest resolution thus far attained of the surface of Venus. And he identified the highlands, the radar bright highlands, as a heavily tectonically altered surface that they call tessera. So here is Ishtar Terra, the big volcanic plateau. Maxwell Montes here. These mountain ranges around the plateau. And here is a close-up view of Acna Montes, which is one of these mountain ranges at the edge of the plateau. So really high resolution with Vignetta, which allowed the scientists, the planetary scientists, to do planetary geology for the first time for Venus in detail. Even though not radars, there is an important element here for radars, because PVO, Vignetta, and Vega probes from the US and Soviet Union were able to land on the surface, and they acquired data about the atmosphere. And the atmosphere of Venus is so thick that there's a little bit of refraction on the radar, on radar waves, especially at the higher frequencies. But the Vega and Vignetta Soviet probes also attained photography or television images of the surface of Venus at different locations. So you can see the range in types of features that are visible. You have scattered rocks that are boulder size, 30 centimeters. This instrument here for radiation is 30 centimeters in length. So that gives a scale to the rocks on the surface. You have some layering, you have some sediment, and of course, the backscatter of radar depends on the texture of the surface, as we know. So a smooth surface is going to produce a lot more backscatter if it's a nadir, or much lower backscatter if it's side-looking, than a surface that is full of boulders, like Vignera 9. And then in 1989, the U.S. launched the Magellan probe to Venus, and here's a Magellan being deployed from the space shuttle. And it used S-band, similar to Vignera, but it produced even higher resolution imagery, now at 75 meter per pixel postings. And the footprint of the altimetry was 20 kilometers with about 100 meters of uncertainty. And it collected data for almost the entire planet, 98% of the surface. And it provided an enormous amount of science with the data set that it created. In fact, we're still using Magellan data and making discoveries about Venus to this day with that data set. So it is currently the best view we have of the Venusian surface. And here's the map of the surface of Venus as seen by Magellan. Here at the top, center top, we have Ishtar Terra, the big plateau with Maxwell Montes. Here, the bright area. And here is Ishtar Terra that we had shown before. And a whole lot more geology that we can now identify between craters, different volcanoes, tectonic features like this big arc here, which is called Artemis. It's a fantastic data set. And in fact, I started my career in planetary science analyzing data from Magellan back in 1997. And here's an example of contrasting the imagery from Vignera and Magellan. On the right, we have imagery from Vignera showing this area, which we call tessera, that is dominated by tectonic folds and tectonic faults. And the same area here in this red box on the right is this entire image here on the lower left of Tellus Tessera, now with Magellan here on the left. And a close-up of the Magellan data set shows all the different folds, and then there's a fold coming here from the northwest to the southeast, a couple of folds, and then there are all of these fractures of the surface here, the faulting from the southwest and northeast. So an incredible data set. And with that, we're able to identify different types of geology on the surface of Venus. One of the things that we use to identify geologic provinces is what we call the physiography. What is the shape, the texture, the topography of different things? So we have the plateau of Ishtar Terra. Aphrodite Terra is actually comprised of 3 plateaus, Western Avda, and Thetis. You have big volcanoes like Hawaii. We have here like we have here on Earth as Hawaii, or the Eastern African Rift. We have here in Atla, and we have here in Beta, and down here in Lada. There are smaller plateaus as well, like Alpha, and these volcanic tectonic features that we call corona of Isla, in Isla Regios, and so forth. Really rich data set that allows us to map Venus, the geology of Venus, to a great detail. So now that we have this data set, I'm going to step a little bit away from radar per se, but focus a little bit more on the planetary science that the radar has enabled us to conduct. So most of the surface of Venus is covered by volcanic plains, which are really smooth and covered over 80% of the surface of Venus. And they tend to be lower than the highlands, the plateaus. But still, that when we look at the data set, we see that there are over 900 craters that we're able to map on the surface of Venus, and here are the crater distribution. And one thing that counting craters allows us to do is to calculate the age of the surface. So we can estimate the frequency of impacts over time in terms of asteroids and meteorites hitting the surface. And the longer the surface has been exposed, the more craters it's going to accumulate. So a surface that has more craters is older than a surface that has fewer craters, which is younger. So what we're able to see is that the age of the surface of Venus is somewhere about 750 million years. So it's not a very old surface. Continents on Earth are, in some locations, billions of years in age. So overall, the entire surface of Venus is relatively young. So Venus has been active to a certain degree, but we still do not understand the activity, the level of activity currently. Not only that, you can see that by understanding and doing statistics on the distribution of craters on the plains, you see that the plains are not of all uniform age. Some areas of the plains are younger, like here, from 500 million years, and some of the plains are older, going to almost 1 billion years in age. So the plains were created not suddenly, but in different stages. And why is that important? That is important because we still do not understand how terrestrial planets work. We see that the Earth has plate tectonics. We'll talk about later. Venus does not appear to have plate tectonics. Mars is different from Earth and Venus in terms of tectonics and volcanic activity. And all of this is tied to how a planet cools off over time. Terrestrial planets are nothing but heat engines. And we don't understand why plate tectonics or how plate tectonics really started on Earth, and why other terrestrial planets do not appear to have plate tectonics. So there's work ongoing to try to understand that. And even if a planet that starts in one way, like in a magma ocean when the surface is completely molten, if it's going to how it transitions from a magma ocean early in its age when it's really, really hot to an Earth-like or a Venus-like situation. Is there an evolutionary path that all terrestrial planets follow? We don't know, but that's what we're trying to understand by studying Venus. And the way that the planet loses its heat is through convection and conduction through the solid outer part. And how the outer part is being recycled back into the hot mantle is part of that heat engine, and increases the efficiency of the internal convection if it's being recycled. So all of these, I'm not going into detail, but just to let you know that radars enable us to help understand what's going on in terms of the inside of the planet as well. So I mentioned plate tectonics. Here's the Magellan topography of Venus. And there's quite a bit of variation in elevation from minus 4.5 all the way to 11 kilometers C in Maxwell Montes. Even though there are these highlands and lowlands and volcanoes and these rifts on the crust of Venus, as we see here on the eastern side of the map, there does not appear to have something like the Earth, the broad continents and the ocean basins, and the system of plate boundaries that we see here in the ocean floor, the middle ocean ridges that breaks the outer rigid part of the Earth, the lithosphere, into different plates. So Venus does not appear to have that, just by looking at the topographic map alone. And here on Earth, of course, the plate tectonics is part of that inner convection that I was talking about, where new crust is being created, oceanic crust is being created at the middle ocean ridge, and it spreads over time, and it subducts under the continental lithosphere or another cooler oceanic lithosphere. So this is part of the recycling of hot material and out, losing heat to space and pushing cold material back into the mantle. And here are a couple of views of this trench area in the western coast of South America and the ridge area of the mid-Atlantic. But there are rifts on Venus, but they don't seem to be organized like in plates like we have here on Earth. So this is possibly a similar process, but not quite identical to Earth. Maybe the crust here, the lithosphere, is spreading. Maybe there's more volcanism around these rifts and allowing heat to come out of the interior of Venus. The other thing that we know is that the plateaus where the tessera, the highly tectonized surface exists, they are older in age than the plains because all the plains inundate and stop right at the tessera. So here's the progression of events on Venus. Tessera were formed, then plains were emplaced, and then later there was rifting. There are also areas of Venus where there's some deformation, compressional deformation on the surface that surround crustal blocks. So this may be an analog to what has happened in the Earth, earlier Earth, when you had microplates and cratons that were colliding and accreting to form the broad continents that we have today. And here's a view of a map of the tessera that I was talking about. We don't know if the tessera occurred only at these plateaus, these high standing areas of. There's quite a bit of tessera underneath the volcanic plains that were just covered by the lava. But the tessera is only 8% of the exposed surface nowadays. And when we study the tessera with the high resolution imagery from Magellan, we see that tessera have quite a bit of range in terms of how they were deformed in their the disposition of the different folds and the different faults, and this would not be possible without radar doing this level of imaging, this level of science and distinction of the different types of tectonics. And even by looking at those images and studying them, we're able to determine whether something deformed first or imply the mechanical properties of the crust, but to a certain extent only, because the Magellan data at 75-meter resolution does not have a high resolution global topography. So it's very hard to sometimes look at the finest details and really understand with certainty what the surface was doing over time. So even though Magellan was this fantastic radar about Venus, we still cannot answer first-order questions about the planet because the resolution of the data between topography and image, there's a contrast in resolutions. And for the imagery, 75 meters is sometimes not enough for us to understand some of these bright lineaments. We don't know if they're high frequency folding or if they're layers. So we really still need even higher resolution to do the kind of science that we need to do in order to understand the evolution of Venus. And to do that, we have a number of missions that are not only proposed, but they've been accepted by NASA, and they're in a certain level of development currently, and they're intended to fly in the early 2030s. The first of these missions is the Veritas mission, which is a NASA mission being developed at the Jet Propulsion Laboratory. And it's going to carry two instruments, a radar and a spectrometer imager. And it's also going to conduct some gravity measurements using the telecom link between the spacecraft and the Earth. And here are some of the questions that Veritas wants to address. what are the different rocks on the surface using the spectrometer, because we don't know if on the surface of Venus it's all basalt or if there's granite. If there is granite like on Earth, it means that the crust of Venus has been recycled in the presence of abundant water. There's no water currently on the surface of Venus, but if we see granite, it would mean that Venus had oceans in the past and that the crust of Venus was being recycled. What is the previous geologic regime on the surface? Did Venus have plate tectonics at one point, or not, or has been the way it is today, or was it something completely different? Whereas the emplacement of the volcanic plains all sudden in rapid stages, or those stages separated by long periods? The crater statistics seems to indicate that there was a long period, but the crater statistics also carry a high degree of uncertainty. Is there a subduction of crust on Venus today, and so forth? Is Venus active? Are there volcanic eruptions occurring today on Venus? These are all first-order questions that we still don't have answer for. And here is just an image of, on the right of this figure here on top, you have the big island of Hawaii. And on the right side of the image, you have the resolution of the Magellan altimetry data. And on the left, we have a simulated Veritas resolution for the island of Hawaii. So you can see the type of improvement that Veritas is going to generate over the previous data set, over the state-of-the-art that is currently the Magellan data set. And here are the resolution of the rock type spectral measurements that are going to be made, so you can distinguish individual lava flows and the volcanic building with respect to the plains. So the interferometric radar from Veritas that is proposed to be used, or it's under development, is a single-pass interferometric radar that is going to produce not only images, but through interferometry, single-pass interferometry, topography data. And that's what this illustration is intended to show. And this data set is going to be global. It's going to cover the entire planet, their radar data. So in preparation for Veritas, the team conducted an analog campaign in Iceland to understand the behavior of X-band and S-band radar waves with different geology on the surface. So the team deployed to Iceland to characterize different volcanic, tectonic, and sedimentary units that are thought to be similar to Venus. And Iceland is great because Iceland has a fresh surface. Volcanism is ongoing, tectonism is ongoing, because it's in this boundary between two plates and the ocean ridge and mid-ocean ridge, and also a mantle, hot plume is also beneath Iceland. So lots of activity there. And because the surface is young, there's very little vegetation for most of the country. So it's a great target for radar. So we employed multi-band airborne radar to map the surface. And with a surface team, we characterized composition, dielectric properties, moisture, roughness, and topography, all of these things that control the backscatter of the radar wave. So the campaign was in collaboration with our colleagues at DLR, the German space agency. They flew their airborne multi-band system called the SAR. Here's an image of the airplane and the radar antennas here on the starboard side of the airplane. He operated at 3 bands for us: X band at 9.6, S band at 3.25, and L band of 1.325 gigahertz. And the bandwidth that we adopted yielded a theoretical resolution of 0.75 meter, but when we process the data, we have 2 meter postings for the radar maps. And the images collected by FSAR span the entire range of incidence angles used both in Magellan and that will be used in Veritas and Envision missions. And I'll talk to Envision shortly. Here's the island of Iceland and the 3 areas that we studied. So the airplanes the airplane, the FSAR did a variety of mapping strips. Each mapping strip is characterized here by this blue rectangle. And inside of this mapping strip, here's the near side and here's the far side, near range and I should say near range and far range of the strip. And in the middle of it is the X-band incidence angle for Veritas. The green is the Magellan-like S-band incidence angle range. So, and multiple strips covered the same piece of the surface with different bands and incidence angles. So you can do quite a bit of modeling of surface and backscatter based on what we got from this campaign. Here, an example of the 3 bands for the lava flows, Askja volcano in Iceland, and we have the X band with very high resolution, and the L band providing quite a bit of contrast for the different flows. And this also allows us to understand how you compare 2 data sets, one in X band like Veritas, and other data sets like Magellan at S band. How do you relate what you see one to the other? So that's a key, crucial aspect of our campaign study. And just for a little bit of flavor here is the some of the surface data we collected, high resolution topography of the surface. So here's Pahoehoe lava flow basalt with lots of folding, fine scale folding. You can see that the side of the square here is 6 meters. Here's the range in elevations. So this is allowing us to understand the backscatter for different surfaces. And here's the range in dielectric constants, the loss term, the imaginary portion of the complex permittivity and moisture contents that we collected at the surface. Now, Veritas is just one of the proposed missions for Venus. There's another one called Envision, which is an European mission for which JPL is building the S-band synthetic aperture radar. But in addition to this imaging radar, which will also do altimetry, Envision is carrying an Italian radar sounder, which you can see the big boom dipole antennas here. So you have the SAR antenna and the boom antenna for high frequency. I think this is going to use 9 megahertz for sounding in the subsurface. Another big difference between Envision and Veritas is that Envision is a targeted mission. It's going to observe only portions of Venus instead of producing a global data set. So the 2 missions, Envision and Veritas, are a really good complement to each other in terms of the types of data they'll collect and the kinds of science we're going to be able to do. And finally, something that I just don't have time to go into, but I want you to be aware is that the Moon and Mars are looming larger and larger in the priorities of the different space programs across the different nations. Part of it is because there is renewed interest in sending people and harvesting resources at these 2 locations, at these 2 planets. So understanding the distribution of water, ice, and resources in the lunar and Martian regolith is crucial. So there's a big effort to develop radar proposals to create instruments to characterize the shallow lunar and Martian subsurface. And I think that's my last slide. Yes.
Thank you. Thank you so much, Dr. Daniel Nunes. Now I'm going to open questions for the audience. Any question, guys?
Very nice presentation, man.
Thank you.
Beyond USA and Europe, is there other, is Russia also intending to do something in Venus? Or is there other country trying to image Venus too?
In terms of other countries, in addition to the US and Europe, I didn't quite understand the question.
No, beyond JPL and ESA, is there other institution trying to map Venus also, or not, or only you?
Currently, in terms of radar mapping, there is a proposal, a plan for both India to launch its own mission with its own radar, and China as well. I am not as aware of those two proposals, those two plans. There are some people here, some of my colleagues that are involved from with the Chinese plan. A colleague of mine at Brown University, and yeah, I was trying to get the mirror effect off, but my apologies. Yeah, so there are, in addition to NASA and ESA, plans by the Chinese and the Indian, and they're all in the similar time frames of the 1930s, to the 2030s. Yes.
And about Mars, where the next mission are planned, and what type of aperture radars are you intending to use there?
So yes, so I could give a second talk just talking about the Martian radars, because there have been 4 Mars radars, 2 orbiting sounders, and 2 ground penetrating radar instruments on the surface. So the sounders were built by the Italians, and one flew in a mission from ESA, and the other flew on a mission from JPL, NASA. The second, the one in the JPL mission is called the Sharad orbital sounder. Sharad is still collecting data, so still active. And in fact, I've had some papers in the analysis of Sharad data. The ground penetrating radars, one is from China, that has operated on the surface of Mars, and the other is from Norway, that is operating on the American rover Perseverance. That is the RIMFAX ground penetrating radar. And RIMFAX is still collecting data. For the future, there's a variety of plans. There's nothing selected, as far as I know. Here on the US side, there's nothing selected. They're talking about P-band imagers and ground penetrating radars, newer sounders. There's a whole lot of discussion right now of what we should do next for at least for the US side. And there are collaborations with the Europeans as well. There's the rover from Rosalind Franklin rover, which is the part of the ESA ExoMars mission that has been delayed, but it's planned to be launched in the early 2030s, I think, or 2028. I lost track of it, but it also carries a ground penetrating radar. So there are a variety of plans being discussed right now, but I'm not aware of a single selection or multiple selections yet.
And this penetration depths, how deep it should be for this mapping? How many tens of meters or hundreds of meters?
So yeah, so science-wise, anything at the surface and below is of interest scientifically. We want to know everything, right? Scientists are never happy with the data they have. They want more, because they want to understand all the different aspects of a planet. Now, a big push right now is to support the presence of humans on both the moon and Mars. And it's already difficult to go to exploit resources deep in the earth, where we have all of the resources and we're operating our natural environment. And so going to the moon and Mars is going to be even harder to extract materials from the subsurface. So to start with, they're probably going to be talking about exploring the top tens of meters only. So a lot of focus is being paid to understanding at high resolution the tens of meters of the top tens of meters of the subsurface.
Yeah, very nice.
Hi, Daniel. Good to see you over across from Unicamp. And
Hi.
hi. I know the topic or talk is terrestrial planets, but I'd like to hear your view on the use of lightweight drone-based radar system on icy satellite like Titan. Of course, I'm talking about Dragonfly mission and missions like that.
Yes. So on Earth, there are multiple applications, of course, from glaciology, archaeology, everything, biomass. So on Earth, we have seen in the last 5 to 10 years the importance of having assets on drones, how much it opens up for us to study the surface of the Earth. And the same thing is for the planet, because I had a study with a postdoc here where we compared the data from the orbital sounder SHARAD that I talked about around Mars with the ground penetrating radar data RIMFAX on Mars as well. So in this paper we contrasted the two data sets, and for RIMFAX we were seeing reflectors at 15 to 20 meters beneath the surface. And by reprocessing the SHARAD data, we were able to attain similar resolutions in terms of range through some educated super resolution reprocessing. And we were not able to detect anything with the reprocessed SHARAD data. And that's because the illumination area of the surface, or the first Fresnel zone from an orbital sounder, is quite wide. So if there's enough variation of the target in that first Fresnel zone, you don't get a coherent reflection. So it's really hard to map certain types of features in the shallow subsurface with orbital sounder. So that's why we have something on the rover. But the rover has limitations on where it can go. It moves very slowly. So if we're able to have very lightweight hardware that is moving about, being in a flying platform or a hopping platform, that would broaden, like it has done here on Earth, broaden our ability to go to places and collect data more efficiently. It's the same thing. It applies to planets as much as it has been applicable to here on Earth.
Thank you.
Thank you. Any other question?
Hello, Daniel. This is Hugo. Excellent talk. Congratulations. Well, we know that our normal system operates in three band frequencies, C, L, and P. Have you heard of any other institute or group, or even at NASA trying to use the P bands, and how this can be interesting for you and your research?
So I know there are different groups working on lightweight radars to deploy to drones and light platforms, flying platforms. Some of them are more interested in the surface per se, the surface reflection, because they're mapping moisture content, for example. Some of the others are not P-band. They could be modified to be P-band, but I'm not aware of a P-band system. What I would like to stress, and that's why we've been talking, Hugo, is the thing that really attracted me to your system is the multi-band aspect. So I think there's great power in having a multi-band system that is lightweight and co-located in a single platform so you can collect the data at the same time at these different wavelengths. So because then you're not only understanding the surface, but also different depths of the subsurface. So when you're doing inversions, having the different wavelengths and different depths of penetration is extremely useful.
Thank you. Thank you.
Thank you, Professor. Any other question?
Daniel, today afternoon, we will have a talk of the German Geoscience Institute, GFC, from Potsdam, near Berlin. And they did, they could map the lava undergrounds, which is some volcanoes in Iceland. And they have also some publication about that. I don't know if you have seen this publication.
Yes, we have, and in fact, we had a telecon last week to discuss a little bit of what I've done and what they have done as well, and how we can collaborate to collect more data. And they're going to send me some samples here, because one of the things I've been doing here at work is characterizing the dielectric properties of samples in the laboratory. So I'm really looking forward to continuing my conversation with them, because I think there's quite a bit of potential for collaboration.
Yeah, very nice. Excellent.
Thank you. Any other question? No? Dr. Daniel Nunes, thank you very much once again. A round of applause for him, please. Thank you. No more questions, because it's time to lunch, to have lunch. And maybe this is the reason why people are not asking so many questions. But thank you so much.
That now I wish I were there. You're having lunch. Good food.
Guys, at 2 p.m. we are back.